Hi guys, so welcome to the video. In the previous video I talked about rejection sampling algorithm, the theory behind it, and in this video we're gonna code it. We'll be using Python, so I hope you're at least somewhat familiar with it. If not, then I think you will still understand what's going on. I already pre-coded everything in this Jupyter notebook because if I coded live I could embarrass myself. That's not something you want to see, or maybe you, but not me. So okay, so let's get to it. The first cell is just some initialization of Python. So the second cell is this really interesting one. So here we define some ugly function f, and if you look closer what's going on, so you can see that this function is 0 when the input x is less than -2. Between -2 and 0 it returns a normal probability density function at x. So this is like really ugly. Between 0 and 2 it returns 0.2 times square root of x, and between 2 and 4 it returns natural logarithm of x times 0.11, and it's 0 elsewhere. So if we visualize it, it looks something like this. It's like 3, I don't know, fingers. It's a really nasty function. Okay, so let's try to simulate from this function using rejection sampling algorithm. So first, we have to choose the overlying density function g. So in our case, it will be a uniform distribution from -5 to 5. So if we plot it, it looks something like this, right? -5 to 5, and at each point it's 0.1. And if you recall, this should be overlying function, but here it's 0.1, whereas here the maximum is 0.4. So the overlying function is not really overlying, it's somewhere in here, and we needed to overlay it, so we need it to be somewhere around this value. So how to do it is the scaling factor. So here we can calculate the scaling factor, and I calculate it as follows. Take the maximum of this term. If we plot it, then you can see that the m times g, m times the overlying distribution, is it's dominating the f function which we want to sample from. So at each point the blue line is higher than this yellow line. And now we can, if we use 1, it's really tight, there's no gap between the maximum of x and minimum of mgx. So maybe we can give it a little bit of bumper. We introduce this gap here. We can even introduce much bigger, wider gap using 5 instead of 1.1. And you can see that now the mgx is really dominating the fx. It's much the gap is just really wide. And if you recall, this is not something we want, so let's proceed with 1.1. So this is this is the setup we will proceed with. And now this is the heart of the algorithm. So x is basically just a container or a list that we will fill with the accepted samples. N is number we want to run this algorithm, so how many times you want to run this loop. And loop is very simple. So first we sample from the overlying density, which is, if you recall, -5 to 5 uniform. So we get a sample, and then we do this comparison, and if it's true, then we append x to the list, and if it's not true, we do nothing, aka we reject the sample. So this is accept or do nothing, aka reject. So let's run this one. And as you can see, it's not real instant, so it takes some time, even though it's just 10,000 loops, which usually ends up pretty fast. And you can see that the ratio is just 25%, meaning out of the 10,000 samples we generated here, only 2,500 really was accepted, rest was rejected. But this is still a nice ratio, because for rejection sampling this is okay. Now let's plot the results. So on the right side you have the original f function, on the left side, and on the right side you have the samples. And as you can see, it's quite okay, it matches quite well. You can see this big spike here, the middle spike, and a little bit of the right spike, exactly as here. So it works, good news. And if you look at how we got to the result, it's just this little loop right here. So it's really nice. It's really simple algorithm, and you can use it quite efficiently. Easy to implement. Now, final thing, let's just change the gap here. So let's make the gap wider. And if you recall, this should cripple the accepted ratio. So if you run this one, we can see that suddenly the accepted ratio is just 5%. So the wide gap just cracked the algorithm. And if we draw the results, it's pretty similar, which was expected, but much less samples. And if we do something like this, something like this, meaning suddenly it's not really overlay intensity, this algorithm should be broken. It runs, yeah, we have really nice accepted ratio, but the results should be really, yes, you can see that it just cut this top of us, like cut exactly as here. Yeah, so we got this instead of this. So this is why you have to choose the scaling factor really carefully, because it can, this setup will fuck you up, and if you make the wide gap, it will just not be really accepting a lot. Okay, so that's it. The very last cell is just it's for like Python enthusiasts. You can code this for loop as NumPy vectorized. You can vectorize it, and this is how it looks like. So it should give exactly the same results. It does, but it should run much faster because here is no for loop. This is all in NumPy and it's vectorized. Okay, so that's it, guys. Hope you enjoyed it. I will pass this vectorized version, this vectorized snippet, into the description so you can use it. And okay, this concludes the series. I hope you liked it. If you liked it, then give it a like, and maybe we will see each other next time. So see you.